Okay. All right, so hopefully this made sense. Okay, let's go to the next problem. Okay, so let's see what this structure is going to be. Okay, so the molecular formula is C7H16. Now, one mistake students often do is they try to muscle their way around by drawing all possible structures for a given molecular formula and then see which matches. Don't do it that way. Okay, that's going to be too cumbersome. It will be too time consuming. The smart way to do is piece together the different groups you see in a molecule based on the NMR spectrum, and then see what matches what you have. Okay, that's what I would say. That being said, when you're given a formula, try to find out the double bond equivalence. Double bond equivalence, which I solved an example last time. One of the videos the one video I said there is a YouTube channel video there that also shows you how to calculate double bond equivalence. So use that to see how many double bonds or cyclic structures you're going to have. Okay. Now that being said, how many double bond equivalents does this molecule have? So this one has 0 double bond equivalents because an oxygen can essentially be ignored. Okay, when you're calculating the double bond equivalents. So if we have 7 carbons, right, it is going to have maximum of 16 hydrogens. So it's not going to have a cyclic structure. It's not going to have a double bond. Okay, because if you have 7 carbons and you do not have any single bonds at all in the molecule and no cycle, it is going to have 16 based on the homologous series formula, which is CnH2n plus 2, right? 2n plus 2 formula tells you that the double bond equivalent is 0. So I'm going to move forward here. So this doesn't have any double bond. That's one thing you want to start with. Okay. Now the next thing is you have a triplet, and here you have a quartet. Okay. A triplet quartet. A triplet quartet is a classic ethyl group. So when you have a triplet quartet, you can be fairly certain you have an ethyl group, because an ethyl group, right? If we have a CH2 and a CH3 and nothing else here, right? Nothing else here. If this is not going to split these 2 hydrogens anymore, then the ethyl group is going to have a triplet quartet pattern. Okay, these 2 CH2s are going to make this into a triplet. Okay, and these 3 CH3s are going to hydrogens are going to make this into a quartet. Okay, into a quartet. And since this is primary, this is going to be between 0.5 to 1.2, 1.3. All right. So this one is going to be typically, it's going to be, if this is a carbon, right? This is going to be around 1.9 or less than 2.0, right? But here, as you can see here, this is a 3.5. That means this hydrogen is attached to an electronegative element. So most likely that's an oxygen. Okay. That's what you should see. Now we already have figured out the ethyl group, okay, based on the triplet quartet pattern. Now you have the remaining part of the alkyl chain, which is what? You have taken care of 2 carbons and an oxygen, okay? Now we have 5 more carbons to account for. And the 5 more carbons are attached to hydrogens, which give you a singlet and a singlet, okay? So you see a singlet of 9 hydrogens and see a singlet of only 2 hydrogens on the other side. And this singlet also is at a very high ppm value, okay? So that tells you that on one hand, you have an ethyl. On the other hand, you have 2 hydrogens, which are directly attached to the oxygen as well. And then you have an alkyl chain. So this is the CH2, CH3 of the ethyl group. These are the 3 hydrogens, okay? And these 2 hydrogens here attached to ethyl. So you have taken care of 3 carbons, right? And you now have to worry about 4 more carbons. When you see a singlet for 9 hydrogens, okay, singlet for 9 hydrogens, what are these hydrogens going to correspond to? Can you guys tell me? It's a single peak, 9 hydrogens. What are they going to be? It means you have 3 CH3 groups. I see a direct message. Okay. Yeah. Yeah. So it means tertiary butyl. Yeah, exactly. You have tertiary butyl group, right? So that means you have carbon with 3 CH3s here. Okay. 3 CH3s here, and all of them are going to be a singlet because this carbon does not have any hydrogen. Now, this is one of the most easily confusable things for students, because they would see this hydrogen here and they will say, why is this CH3 appearing as a singlet, right? Tertiary butyl appears as a singlet because this carbon is what matters, and what we have there matters. This one does not have a hydrogen, okay, because it already has 4 bonds. Therefore, this is a singlet. This is a singlet because, again, these cannot split here and so on and so forth. That is that. So based on proton alone, you can decide what you have. So look at the multiplicities first, and then look at the ppm values also, right? And then go based off of that. Now, if you look at the carbon NMR, you see these carbons here. That is the one that are the carbons attached to the oxygen, okay, directly. And these three carbons are A, B, right, and C. So let me make a different color. So that carbon, and that, sorry, my bad. And that carbon. These are the ones that are in the alkyl part of the molecule, okay? All right, so that's that. Hopefully, and so yeah, even without looking at all the information, you can solve this problem. But here, let's see what this tells you. The molecule does not show a C double bond O because C double bond O appears at a 1700 region in the IR spectrum. Okay, in IR, you do not see a 1700, which means you do not have a carbonyl. You do not have a carbonyl, be it aldehyde or ketone, or maybe even a ester. You don't see that. Okay, and you don't see a 3300. That's very valuable information because 3300 is what corresponds to a alcohol group. Okay, so this problem can be solved only with proton NMR. C13 adds a lot more. And if you know IR and carbon 13, sorry, IR also, it makes it even more easy to solve. So you don't have to worry about writing alcohol structures, right? You don't have to write alcohol, you don't have to write carbonyls, all that. So it essentially, when you have an oxygen, it's not an alcohol, it's not a carbonyl. You're left with potential, an ether. Okay, so that's the way you look at it. Now, one more advice I will give you is students write off spectroscopy because they think it is difficult, but spectroscopy is one of the easiest things you can solve because these things like 1700 signal in IR, 3300 in IR, they are very useful identification tools. Okay, so you only need to know 5 or 6 pieces of information for each spectroscopy. Just make sure you memorize that, and you will be able to solve a lot of problems when it comes to spectroscopy. Okay, all right. So that's the structure that we had. Okay. All right. Now let's look at next this. So what spectroscopy is this? Okay. This is your mass spec. When you see M by Z, right? When you see M by Z, that means you have a mass spectrometry problem. Okay. You have a mass spectrometry problem. M by Z stands for mass to charge ratio. All right. So if we have a molecule that, say, for example, has a mass of 100, okay, atomic mass units, right? And if it has 2 charges, okay, 2 positive charges, right? That means you will see a signal at 50 M by Z. That's what it means. So make sure you understand that, okay? But generally, what we see, generally, not always, most 99% of the time, what you see is essentially a molecule with 1 positive charge. So whatever number you see can be assumed to be assumed, okay? Those assumptions can sometimes be wrong, but they can be assumed to be the molecular weight of that fragment. Okay, so keep that in mind. Okay, now let's look at this. So as I told, in spectroscopy, you are often tested on very classic set of problems, classic set of concepts. Okay, so one of those things is this. You are given a spectrum. You see a 51 and something slightly less than that. Usually these 2 satellite peaks, they don't really mean much. Don't worry too much about it. When you're looking at 2 peaks, right, there are isotopes of isotopic peaks. Always look for the isotopic peaks towards the right-hand side end of the spectrum. Don't worry about isotopic peaks in the other part of the spectrum. Don't confuse yourself. Look at that end of the spectrum. All right. So here you see 2 isotopic peaks. Okay, that is a classic sign for a specific group in a molecule. All right. Okay. And then you see a 77. Based on these 2 information, right? Based on these 2 information, try to answer this question. So which of the following statements is or are true about the mass spectrum? Okay, the molecule contains a hydroxy group, right? If you want to know whether a molecule contains a hydroxy group or not, what you should see is, you should see whether you have an M plus minus 17. Okay, so what I mean by that is, if we have a hydroxy group, right, you'll see a molecular ion peak, and then you'll see a molecular ion peak minus 17, right, in the mass spectrum, which corresponds to an OH group. Okay, which corresponds to an OH group. Remember last time I told you to know the periodic table and know the atomic masses of a few elements, right? So you can pull out the periodic table. It's going to waste you some time. But if you know that carbon's atomic number is 6, its atomic mass is 12, the majority isotope, right? Hydrogen is 1 and 1, atomic number, atomic mass is 1, okay? Oxygen, right, is atomic number 8 and atomic mass 16. That's the major isotope, okay? Atomic mass. So most of oxygen in nature is atomic mass 16, all right? So oxygen and hydrogen is going to be 17. So if you see an M plus, right, an M plus minus 17, that means you have hydroxy group, which you do not have here. Therefore, this is not correct, okay? All right, the molecule contains a bromine atom. Okay, this is true based on this mass spec because bromine has two isotopes in nature, which is Br79, okay, and Br81. Br79 and Br81, okay? And the thing about bromine is, of course, all atoms have isotopes, right? Why am I talking about bromine specifically, okay? If you look at most elements, right, that are small elements, like I'm talking about the first row and second row and almost third row, right? There, only one isotope is going to be the major isotope, the other one is going to be small. But when it comes to bromine, it's almost a 1-to-1. In nature, you see almost like 51 to 49% of bromine 79 and bromine 81. That's what you're seeing here. Okay, so this tells you that you have a bromine atom in the molecule. So hopefully I'm like, this makes sense. Okay, large atoms, they have multiple isotopes which are similar percentages. They're not like predominantly one, but smaller atoms, they have predominantly one isotope. If you look at carbon, 99.9% is carbon 12. Okay, carbon 13 is going to be less than 1%. Hydrogen, again, 99.9% is proton, 1H, and 0.01% is deuterium, and so on and so forth. Same thing for oxygen. Whereas for bromine, that is a very marked feature. So when you see an M and M plus 2, right, almost equal height, that means you have a bromine in the molecule, a very classic sign, all right? And another sign that kind of adds to this is you see a huge difference between the molecular ion peak and the next fragment, okay? So this is an M and M plus 1, 1-to-1 peak ratio, and also almost an 80 difference, right? So this is what, 156, 77, okay? 77 plus 80 is 157, right? So you can see that. If you see an 80 missing mass, that also confirms that you have a bromine, okay? So when you see these two, you can be sure about that. All right, and what does 77 correspond to? 77 often corresponds to a phenyl ring, okay? A phenyl ring. So it has a bromine. The molecule is an alkene, not necessarily, right? Not necessarily. You cannot say from a mass spec whether you have an alkene or not, right? But when you see a 77, you can say that you have an aromatic compound. So that's what that is, okay? So D is true, B is true, okay? It is capable of rearranging to McLafferty. I'll tell you about McLafferty because I don't want to talk about that separately here. But you should look for that sign also if the question asks for that. It contains a carbonyl group. Again, we cannot say that based on the mass spec. So B and D are the two correct options. Okay. All right. So next, let us look at this. I don't want to make the each problem too big of a discussion, right? Look at the same signs as the previous problem and let's see if we can answer what we see here, okay? Now I want to ask a simple question. Do you guys think this molecule has a bromine in it? Do you guys think this molecule has a bromine in it? Yeah, so no, it does not have a bromine because you do not see a peak height that is 1-to-1. But what you see here is again an M and M plus 3. You see an M, right? And M plus 3. Sorry, M plus 2, right? That's of a certain peak height, okay? It's almost 1 to 1/3. If you look at this, 1, 2, 3. So this is 1, this is 1/3. What does that tell you? It tells you that it is possibly a chlorine. I don't want to say it is definitely a chlorine. It is possibly a chlorine. Okay, if you see a 1 to 1/3, it's chlorine because this is molecule where chlorine has the molecular ion peak is chlorine 35, right? And the same could be molecule with a chlorine 37, okay, with the dot plus, right? Remember, without a positive charge, you're not going to see a mass spec, okay? They all have to be ions. So this is an M with a chlorine 35, and this is M with a chlorine 37. And in nature, right, you see chlorine 35 as about 66% and chlorine 37 is about 33%, which is the reason for this M and M plus 3P if it has chlorine, right? So once you see a 1/3, the next thing you want to see is if there is a M minus 35 and M minus 37, right? That's what you should see next, okay? And if you look at this, that's what that corresponds to, okay? You don't always necessarily have to see the immediate peak as an M minus 35. It doesn't have to happen, right? What I'm trying to say is, let's first look at this, right? So you have a 91, okay? Sorry, yeah, 91, 93, and you have 55, right? So 91 minus 35, let's say, is going to be 90 minus 35 is going to be 65. And 35, sorry, it's going to be 55, right? Sorry, not 65, 55. And if we have like one less, it's going to be 54, right? So it's approximately there, okay? So, sorry, 66 and yeah, it's approximately there, right? So this does correspond to a chlorine, as you can see, okay? Now, what does this correspond to? What is this peak then, right? So you can have a molecule where you have a chlorine, right? And if you lose the chlorine, you get an M minus 35. Okay, when this is chlorine, this is M plus. When you lose the chlorine, that is M minus 35. But you can take the same molecule, and even before you lose the chlorine, you can lose the other side of the molecule, which gives you a smaller fragment, right? From this, that is not a 35. Okay, therefore, you should not always look for an M and an M minus 35 for the immediate peaks. You can also look for peaks that are going to be a loss of a group on the other side, okay? So 91 minus 69 is going to be about what? 90 minus 69 is going to be 21, 22, right? So 22 is almost, right? It's a CH3, CH2, an ethyl group, okay? So that could be the reason why you're seeing that, okay? So that's basically what you should look for in a mass spec, okay? All right, almost a CH3, almost an ethyl group, okay? All right, so that's that. Now let's go back to the molecule. The molecule contains a hydroxy group. No, it does not. You don't see an M and M minus 17. You don't see that. You will always see if you have hydroxy group, because the hydroxy is one of the easiest group to lose. You have a chlorine, that is right, okay? The molecule is an alkene. You cannot say that for sure. It's not easy to say. It does not have an aromatic compound. If it has an aromatic, which mostly is a benzene, right? Not always a benzene, but mostly benzene, you will see a 77, right? You don't see a 77. Therefore, it is not an aromatic containing molecule. It is capable of McLafferty, not yet, right? I'll tell you what is a McLafferty. And it is most likely haloalkane. That's right, okay? Because we also see a loss of a CH3 something, right? And it contains fluorine. Fluorine is not that easily visible, right? So it is not that. So B and F are the right options. Okay. So hopefully I'm not going too fast. I'm trying to cover more content, but if I'm going fast, please let me know, okay? All right, okay. So now let us look at a McLafferty rearrangement problem, okay? So it's a statement problem, so let's read this, okay? Okay, so McLafferty rearrangement is a reaction that is observed in mass spectrometry during the fragmentation or dissociation of an organic molecule, okay? So dissociation meaning the molecule breaks into large fragments, okay? It is sometimes found that a molecule contains a keto group, okay, that undergoes beta cleavage. So it's mostly seen in molecule that contains a keto group, okay? All right, with the gain of a hydrogen, gamma hydrogen atom. So the molecule loses a big fragment and also gains hydrogen. That's what it tells you, okay? And this was reported by Anthony Nicholas from Australia, right? This rearrangement takes place by a radical or ionic mechanism, okay? All right, and here's the scheme of the reaction, right? You have a ketone, and when it comes to ketone, this is the alpha carbon, right? And that is the beta carbon, all right? Sorry, this is the alpha carbon, right? Beta carbon, and this is the gamma carbon, okay? So alpha, beta, my bad again. Alpha here, beta here, and a gamma carbon, all right? So that carbon gives a hydrogen, okay? All right. And what you see here happening here is you are breaking a carbon-carbon bond that is one carbon away from the alpha carbon. So you're breaking that bond. You're breaking that bond, okay? So that's your McLafferty rearrangement, and you're losing a group in the molecule. So you're breaking that bond, and you are retaining this group. So C double bond O with a carbon is what you're retaining, okay? So based on that, we should be able to answer this question. So based on the above information and your knowledge of the working principle of mass spectrometry, right, which more than one of the following structural information could be deduced from the spectrometry of phenylbutyl ketone. So this is the phenyl ring, and this is 1, 2, 3, 4. This is not butyl, by the way. This is 1, 2, 3, 4, 5. Phenyl pentyl ketone. Okay, that's wrong there. So please make note of that. Okay, phenyl 1, 2, 3, 4, 5 pentyl ketone. Okay, so give me a second. All right, so let's say which of these options is correct. Okay, based on this information. This is not butyl, by the way. This is pentyl. Okay, so signal at M by Z 186 would be observed for the molecular ion. Okay, that's the first statement. So to be able to answer this question, right? So even though you see McLafferty rearrangement, it doesn't mean you will not see the molecular ion. You will still see the molecular ion that corresponds to the whole molecular mass. Okay, that's also going to be there. Okay, so but it's not going to be a large peak. That's what I would say. So in a mass spec, right, you have what is called as a base peak, right, and a parent ion peak. The base peak is the tallest peak, and the parent ion peak is the heaviest peak, but often a smaller peak. All right. Sometimes you see a mass spec where this peak is the largest peak and also the heaviest peak. So base peak and molecular ion peak could be the same thing, but a base peak is the tallest peak, and the base peak is often the most stable species, right? So when you see a molecule at the McLafferty rearrangement, you will see a base peak that is not the molecular ion peak. So this is going to be essentially the tallest peak, and the molecular ion peak is going to be the one that is the heaviest peak. Okay, so that's that. Okay, so signal at M by Z 186 would be observed for the molecular ion peak. So which means you have to calculate the molar mass of this compound. So if you look at the molar mass, that is 77 for the phenyl ring and 28 for the carbonyl. So by the way, it's good to kind of memorize these things. Okay, 77 for the phenyl ring, 28 for carbon 12. Oxygen 16, right? So 28, and then 1, 2, 3, 4. So if you have 14 times 4, right? Because each CH2 is 14, that is going to be 56, and then a 15, which is a CH3 for a methyl group, right? So 11 plus 8 is 19, plus 7 is 26. So 6, 2, 7 plus 4, 11, 11 plus 6 is going to be 17, right? So that is 176, okay? So 186 is what they show here, which means that is not the right answer. You will see a M by Z for 176, not 186. So essentially like adding things up, okay? A McLafferty signal for a neutral ethylene would be observed that detaches from the molecular ion. So based on this, right, you will not, even though ethylene goes away, you're not going to see this in the mass spec because this does not have a charge. So therefore, you will not see a neutral molecule in a mass spectrometry. So that is not correct as well, okay? A signal corresponding to the benzoyl fragment, phenyl with a C double bond O. Benzoyl is a phenyl with a C double bond O. Okay. Phenyl with a C double bond O, right, is that. Okay. So you will see a benzoyl ion fragment that would be observed at 77. So even though benzoyl fragment will be seen, it is not going to be at 77. It is going to be 77 plus 28, which is 105. So benzoyl fragment will be seen at a 105, not a 77. So that is not the right answer as well. Okay. So let us look at this. A McLafferty signal will be observed at 148, corresponding to the loss of the ethylene group in the molecule. So now let's look at this carefully. Okay. So if you lose an ethylene, which is going to be CH2, right? That is 14, which is 28, right? 28. So if you take 176, right, and subtract 28, that is going to be 8, 6, this is 148, yes, right? So you'll see if you subtract ethylene, it is going to be 148. That is true. But you're not going to lose an ethylene group here. You're going to break this bond here, and this whole unit will go away. This whole unit will go away, which is not an ethylene group. In this case, it's an ethylene group because it has only 3 carbons, right? But here it is a 5 carbon chain of which you're breaking that bond, and this is 1, 2, 3, 4. You are losing a 4 carbon unit, not a 2 carbon unit, because it's not ethylene, it is CH2CH with 2 other carbons. Therefore, this cannot be the right answer as well. Okay. Let's see. A McClure-40 signal will be seen at 120, right, corresponding to the loss of the butene unit from the molecule, right? This will be correct. This will be the right option. So if you count for the carbons and hydrogens, that will be a butene structure. It will correspond to about 56, right? And that will be your McClure-40 signal. So this is the only right option for this question, okay? For this question. So that's that. And yeah, for this problem, make one more, what I would say, correction. It's if more than one, possibly more than one or something like that. It's not more than one, maybe more than one, okay? All right. So that's that. I made the problem and I made a mistake, like in the wording. Okay, so that's that. Hopefully it makes sense. Now, what I want to do is look at some IR problems. Okay, we have 20 more minutes before the break, so let's kind of rush through at a reasonable pace, I would say, for the remaining spectroscopy problems. Now, I want you guys to answer this question based on what you know about IR. Okay, so you are given an IR. I will explain the features of the IR, and I want you to answer the question. Okay, so you have a CH stretch. Okay, what kind of CH it is, we will talk about that. And you also see a C double bond O stretch. Okay, what kind of C double bond O it is, we will talk about that. But these are the two major things. All right, and usually in an IR, anything less than 1200 you can ignore. Okay, anything less than 1200 you can ignore. All right, so and it's not always to scale, by the way. That's kind of a weird thing that is in IR. So this may be 1000, I don't know. But these are the two prominent features. Okay, let's kind of look at that first. So you have an IR that has a signals, majority of signals that are at 2991. Okay, so if you look at 3000, this is 3000, right? 2000, 3000, 4000. If you draw a straight line, you will see all the signals are below 3000 in this CH stretch region. Okay, stretching, you're talking about CH stretching in and out. You're not talking about bending or any other modes of vibration. You have carbonyl that has signal at 1715. So based on that, I just want you to answer one question. Do you think it could be this structure? Do you think it could be this structure? What do you guys think? Can I get an answer? Hopefully the question makes sense. Okay. Okay. Can somebody answer this question? Is this a possible structure for this IR? Okay. It's not going to be a possible structure. All right. I will tell you why. Because when you have, so CHs that is below 3000, right? CH is below 3000. All those CHs have to be carbons that are hydrogen carbon stretches that are sp3 carbons. Okay, when you have CH that is above 3000, right? When you have CHs that is above 3000, those CH stretches correspond to carbons that are sp2 hybridized. Okay, when you have alkene carbon, right, or an aromatic carbon, those CH stretches are going to be the ones that are above 3000. So this 3000 mark is a distinct mark that you can easily remember. Everything that is sp3 carbon and a hydrogen attached to it, those carbons are going to be below 3000. Okay, so if you have an aromatic ring or an alkene like that, all right, or an alkene like that, those hydrogen carbon stretches are going to be above 3000. Remember that, it's easy to remember. Okay, all right. So these carbon hydrogens can be below 3000. Yes. Okay, these things will appear below 3000. But if you have this molecule, since it has an aromatic ring, then you should see a CH stretch above 3000. Therefore, this is not correct. This is not correct as well. This is not correct as well. Okay, and this is not correct for more than these two reasons, right? If you have an OH, you will see a broad signal at 3300 like that, okay? That peaks at 3300. So it's not this structure because you don't see an OH, you don't see CHs above 3000, okay, for that. And this could be a possible structure, okay, because you see all carbons that are sp3 hybridized with hydrogens, which could be that. It could be this, okay, but I'll come to that a little later. I mean, it could be this. It could be this structure also, okay, it could be the structure also, right? Based on the CH. All these CHs, they are sp3 hybridized. And this alkene does not have a hydrogen attached to it, right? Therefore, you won't see anything above 3000 because this alkene is tetrasubstituted, right? So you do not have a hydrogen on the alkene, which will appear over there. So this could be a possible structure, but for one thing, okay? It cannot be this, and it cannot be this, okay? Now, why not like, this structure? The reason why it is not this is because at 2400, 2500, you will see a signal for the CH, okay, for the CH stretch. Okay, you will see that, which is not visible here. And it's not this structure because you will see an alkyne stretch at around 2700. Okay, 2700, you will see that, which is not this alkyne. And it's not this structure because if we have this carbonyl, just like in a carbon 13, you see C11O appearing at a lower ppm value than a typical pure carbonyl. When you have a conjugated carbonyl, you will see this C-double-bond-O stretch at around 1690 or 1680, below the 1700 mark, okay? So for that reason, it cannot be this structure, all right? So when you have conjugated ketones with an alkene, like that, right, or a lone pair like that, when these electrons conjugate, that makes this carbon with a double bond O a little weaker. It has partial single bond character, which makes those carbon double bond O's stretch at a lower wave number. So if you have C-double-bond that is conjugated, it will be below 1700. If you have a pure carbonyl, that will be at or above 1700. Okay, therefore, this structure is the most likely structure. All right, this structure is the most likely structure. Now, this one is also pure carbonyl, right? So why is this not the right structure? Because this carbon-carbon double bond appears at 1600, okay, centimeters, which you do not see here, all right, okay, so therefore this cannot be a possible structure as well. So that is why this is the only structure for the molecule, okay. All right, okay, any questions? All right, now what I want to do is I want to ask a question to, this is a bonus question, we don't have multiple choice. I want you to guess what is the possible structure of this molecule. Okay, what is the possible structure of this molecule? Can somebody tell me what is the difference here between 136 and 119? What is the difference? Can somebody tell me? It's an OH, exactly. It's an OH because it is 17. 136 minus 119 is going to be 17. So that's an OH. Okay, good. So now does it mean this is an alcohol? Not necessarily, okay? Let's see why. So between 119 and 91 and 119, right? What is the difference? If this is 120, right, and this is 90, right? We're looking at almost a 30. So 119 minus 91 is a 28, okay? What does a 28 correspond to? What does a 28 correspond to in a mass spec? It corresponds to C-double-bond-O because carbon is 12, oxygen is 16, all right? So when you see a C-double-bond-O, when you see an OH, right, then you should think that it is possibly, not necessarily mandatorily, but possibly a carboxylic acid, okay, because that together is 44, 45, okay, and that is 17 and 28. Therefore, this could be a carboxylic acid, okay, all right. And when you see a 91, these things are memorizations in a way, but it's kind of not that difficult, okay? So if you see 91, that means you possibly have a phenyl ring with a CH3, okay? Because 77 and 15, right, minus a hydrogen is going to be 91. So this could be a molecule that has a CH3 and a phenyl ring, right, and a carboxylic acid. So it could be, right, a carboxylic acid containing molecule like that. All right, it could be that. Now, does it mean no, this cannot be? Like that, right? We cannot say for sure. But that being said, right, most likely it's a carboxylic acid, because carboxylic acids are where you will see an OH and a C double bond O right next to each other, right? And you don't see anything else. You don't see an OH and then sorry, a C double bond O lost first and then an OH and so on and so forth, right? So most likely it is this structure. And if you know more mass spec, you will know that it's not easy to break an OH off an aromatic ring compared to an aliphatic chain, right? So this OH is easy to lose, whereas this OH is not easy to lose and all. Okay, so this is just a bonus discussion. I just want you to know. So if you see an OH and a C double bond O, a 17 and a 28, most likely have a carboxylic acid. Okay, and in reality, yes, this is a carboxylic acid containing molecule. Okay, all right. So I will stop. I will end the spectroscopy problem here, right? So now we have about 10 more minutes. So let us look at some reactions, okay, and some chemistry. Okay, so let's look at this. Okay, so let's look at some answers, or some reactions. Okay, this is also a spectroscopy problem, but it's not going to be too intense as the ones we saw right now. So let's try to answer this question. So given the formula, okay, given the formula, empirical formula C8H10O, okay, and the spectroscopic data below, what is the structure of unknown 1? Okay. Now, one thing I will say, don't sit and count the carbons and hydrogens. Don't do that. Okay. It's always the place where students go. Maybe if you want to eliminate obvious, what I would say, choices, like for example, you have 10 carbons here, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you want to do that, you can say this is not the right structure because this has more hydrogens, right? But don't go there, okay? Unless you want to you're not sure and you want to eliminate this and maybe increase your chances between these three, you can do it that way, right? But if you're better off doing it by looking at the NMR and the IR, you can do it that way, okay? So this tells you that the IR, there's a broad band at 3300. Now what that tells you is you have a hydroxy group in the molecule, okay? So you can easily eliminate that, and you can eliminate that based off the IR alone, and you don't even have to sit and count, okay? Because a hydroxy group has a broad feature at 3300 in the IR spectrum for a hydroxy group, okay? So now it's either this or that. Between B and D, which structure is it? Okay. So it's going to be, okay, this structure. Why? Because you see that at 3.3, you have a quartet, and at 1.8, you have a triplet. Okay, you have a quartet at a low field region, and you have a triplet at a high field region, right? And as you can see, it's a 3.8, okay, and 1.8. 3.8 means you have an an ethyl group, right? And you have a methyl group, which is going to be your triplet quartet, okay? It cannot be this structure again because this one is going to be a singlet, okay? It cannot be this structure because you're going to see two singlets for the methyl groups, and you're not going to see a triplet quartet. And the 7.8, you have two hydrogens, doublet, which is those two hydrogens are the same, right? This is going to be triplet because there is one hydrogen next to it. Sorry, doublet, not triplet, my bad. A doublet because there is one hydrogen next to it. And this hydrogen is also going to be a doublet. Okay, so this is a 7.8 / 7.4, 7.8 / 7.4. So this perfectly matches the NMR spectrum that you see here. So don't have to count. Look at the IR Okay, it has a hydroxy group. So this or that, it has an ethyl group based on this. So that is the right answer. Okay. All right. D. Yeah, thank you. That's the right answer. Okay, so now I'm going to ask you guys to tell me what the multiplicities are, okay, based on what the question says, all right? So on the structure shown, what is the splitting pattern of the most de-shielded proton, which means the proton that has the highest ppm value or the least electron density, okay, for each of these molecules. So for molecule A, the most de-shielded hydrogen is going to be those two hydrogens, right? So what will be the multiplicity? Can somebody tell me? Just for that molecule, what is the multiplicity going to be for this hydrogen? Okay, it's going to be triplet, right? Because there are two hydrogens here. These two hydrogens will make this a triplet. Okay, right. Now here, that is going to be the most de-shielded carbon that makes this the most de-shielded hydrogen, right? And these hydrogens are going to be made into a triplet because you have two hydrogens here, okay? These two hydrogens will make this a triplet as well, okay? That's a triplet, that's a triplet. Here, the most de-shielded hydrogens are going to be, okay, those hydrogens. If you look at aromatic chemistry, right? Sorry, not that, my bad. My bad. This is going to be the most de-shielded, right? Because they're ortho to the nitro group, okay? Because you can write nitro is an electron withdrawing group, right? Which means that will take electrons away from the carbon, putting a positive charge on that carbon. Remember that, okay? So that is going to be the hydrogen that is the most de-shielded. And that is going to be a doublet because you have only one hydrogen next to it, right? So this is the hydrogen that is most de-shielded, and this one hydrogen will make this into a doublet, okay? And here, can you tell me A, B, and C? Between A, B, and C, which is the most de-shielded carbon? Sorry, most de-shielded hydrogen, not carbon, hydrogen. Which is the most de-shielded hydrogen? A, exactly, all right? This carbon's hydrogen, right? We are not talking about carbon spectroscopy here. This carbon's hydrogen is going to appear around 2.1, 2.2 ppm, okay? Whereas this one is going to be around 3.8 ppm, okay? All right, so this is the most de-shielded, and that will be a singlet because you don't have anything. So we have a triplet, doublet, singlet, triplet, doublet, singlet. So triplet, doublet, singlet. So that is the right answer. Okay. All right. So in terms of the carbon-13, right, in this molecule, just this molecule, right, that is going to be the most de-shielded carbon. Would long-range coupling apply to carbon? No, long-range coupling don't apply to carbon. Carbon is much easier than proton and MR, so they won't apply. Okay. Yeah, and so there is not going to be any splitting. We decouple it. Okay, for molecule C, right? So you're talking about whether this carbon will couple with that carbon? No, it won't couple. It will like no. So this is going to be the most de-shielded, followed by that, followed by that, followed by that. Okay, for carbon-13, that's the way it works. Oh, you mean like okay when you write the okay, yes. If you look at like that this carbon is going to be most de-shielded, and then because we can write resonance forms, okay, we can put a positive charge over there, and so on and so forth. But you don't have to worry about having to know to carbon-13 to that extent. Okay, you won't be asked to assign which carbon in the molecule is what. Don't worry about that. But to answer the technical question, yes, that is the most electron deficient carbon, right? Compared to so next, this is going to be the next most electron deficient, and then this is going to be the next most electron deficient. This one is going to be slightly more electron deficient. That one is going to be slightly more electron deficient. Okay. Okay. All right. For which of the below compounds will two chair conformers be approximately the same energy? Okay, so we have to see which two chair conformers for the molecule will be the same energy. So the background is you have, say for example, methyl cyclohexane. This can exist in a different conformation, right? Where this carbon can come down, this can go up for a ring flip, right? And you can have the same methyl group appear in the equatorial position, okay? It can appear in the equatorial position. So there's a ring flip and you can have two chair conformations for the same molecule, assuming like, the boat conformation is not stable, all right? Okay, so based on that, which two conformations will have the same energy? Which one do you guys think is the right answer here for these four molecules? All right, so any answers? Okay, so I'm gonna solve like now. I'm gonna just talk about one molecule, and maybe you can tell me the right answer. Okay, I see C as a possible answer. Okay, let's look at that. Okay, yeah, let me look at C, and then I'll go to the other ones, right? So if you look at C, since I got an answer, right, we have a methyl group in the axial position. We have a methyl group here in the equatorial position, right? CH3. So if this molecule undergoes a ring flip, right? So let me draw this out first. We have an equatorial, and then we have an axial, right? So if you pull this carbon down and pull this carbon up, you will get to a conformation where the molecule is going to looks like this, right? So here, this methyl is going to go axial and this methyl is going to go equatorial, which is same as this. Okay, remember axial, there's a 1-3 interaction, which makes the axial less stable, right? But when this goes equatorial, this is going to go, when this goes axial, this is going to go equatorial. Therefore, you're always going to have one axial, one equatorial, which makes this the right answer. Let's take, for example, A, right? So here, if you look at this, if you draw the other chair conformation, this methyl is going to go axial. Right now, it is equatorial, right? And this methyl is going to go, this is the way it is drawn, right? The way it is drawn, this has to be axial. This is equatorial, right? Yeah, so this is also going to go axial, okay? This is also going to go axial, right? So this is going to be a lot more unstable and this is going to be a lot more stable, okay? Which makes these two different energies, Whereas here, for C, they are the same energy. The other molecules, you will see, we will face the same situation as well, okay? So therefore, that is the right answer, okay? All right, so let us take a break and then we will come back and we will continue the discussion, okay? So right now it is 7:32, so let's meet at 7:40.